Can you hear that? Can you hear those applause?
Yeah.
All right, so all I can see is my RStudio screen. I think we were going to start with, if you go to ldecola.net, which is my personal website, you can scroll down, or just the 3 or 4 lines from the top is a link called 6 World Series, which is my colloquial name for this project. So the data and the script that I'm going to run are online. The script changes from month to month, but the data, the database, which is a CSV file, I typically update about once a year when the new data come through. So you can see there that the data are on ldecola.net/project/global data and the script. And the only thing I really need out of the ordinary to run this script is the forecast library, which I'm not going to use until later, but I'll run it right now. So I'm going to install forecast. And I have some graphical parameters that I like to use, which I've just installed as a function. And then we go to the URL. So one of the things I really like about R and RStudio is that you can read data online. You can read script, you can read text files and CSV files. And so I actually run read CSV and I get the data. And there are the data sets. It's a data frame with 7 columns. The first column is year, and the second through the 7th column are in order watts per meter squared, which is the solar constant, so-called solar constant. Global temperature in degrees anomaly from, I think, about 1960. Precipitation, the most first few observations are NAs, but that's millimeters per day. The 5th column is billions of people, starting at about 2.6 billion. The second to last column is gigatons of carbon emissions from the planet. And the last column is parts per million of CO2 in the atmosphere. And if you go to the website, you can see the sources for all those data sets and more explanations of what they are. So let's just look at a quick summary of the data. You can see, for example, that we have a considerable number of NAs for the precipitation data. The first 30 years or so are missing. I used to use an older data set that was more consistent throughout the time, but we don't, this is a better data set that's come recommended to me by NASA. And then the other data sets have missing values. The last observation is actually, I think, about 2018. So what we're going to do is just look at a plot of the data, just an absolutely naive plot of the data. If I just do plot global, and we get a mess on the bottom screen there, which I will enlarge. So that one of the great things about R is that it'll plot almost anything, no matter how stupid the idea is. So this is a way of looking at a scatter diagram among the 7 variables. And you can see certain obvious patterns here on the upper row and the left-hand column, and the lower right-hand column. You see some consistent, strong correlations among the variables. Towards the middle of that plot, you don't see very much consistency, and our second column, watts per meter squared, doesn't seem to show much at all. But let's make a time series out of those. So we'll use the TS function to create a time series. All TS needs is a data matrix or a data frame, and it needs the value of the first observation. So we'll take that and create a structure called global.ts. I like to use the abbreviation after the data structure so that I know that it's a time series, so I don't do anything stupid with it. And if we look at the structure of that time series, it's very simple. It's 71 columns and 6 columns and 71 rows, and it has those 6 I selected those 6 columns, and their names are there. I must apologize for the obscurity of the names of those variables, because but it's pretty useful, because when we're going to start doing plots, we can see what the units are. So I'll run my graphical parameters, and then we'll look at a plot of the data, and I'll enlarge that plot. The reason I developed this project, I developed it several years ago when I was teaching, and for those of you who are taking notes, I recommend looking up the Kreplach joke, K-R-E-P-L-E-C-H, the Kreplach joke. The idea behind it was to get people to look at the 6 significant global data series, and instead of arguing about whether humans are or are not changing the global climate, they should at least look at some of the important data series and come to some agreement about what's going on. So that was my policy goal, or my political goal, in getting people and looking at this data. So again, there on the left are watts per meter squared of the solar constant, so-called solar constant. Temperature anomalies, I think, as I said, around 1960 in Celsius. Each degree represents about 2 degrees Fahrenheit. Millimeters per day of anomaly rainfall. And then on the right column are population of the planet. The second graph on the right is gigatons of carbon in the atmosphere, or put off, emitted into the atmosphere. And in the last column is the well-known Mauna Loa CO2 parts per million plot that was originally developed by Keating in the 1950s. And again, just to review, the dimensions of these variables are listed on the top. So let's just select one of them. Now, if you were going to run this code, what I'm doing is I'm selecting the second variable, in other words, the Celsius, which is obviously in many ways the most interesting one. So if you look at the plot, we're going to select the second variable, but you could certainly look at the rainfall data on the lower column. That's a particularly interesting data series to look at. You could also look at the watts per meter constant. You could look at any one of those 6 variables, but I'm going to just select the second column of the time series, and if I do that, I'm going to call it. I'm going to create a variable called a string variable, namely the units. I'm going to use that variable to select the column from the series. I'm going to put a title and a source on my data set, and then there is the summary statistics. We have 2 missing values, and we have a value of Celsius that goes from minus 0.2 degrees to about 1 degree Celsius. So the range is about 1.2 degrees over the period, and you can see that from the plot. So I'm going to show a histogram. The first time we're going to look at the histogram, I'm not sure. I'm going to run my graphics program again, my graphics function again, just to make sure I've got the right. I keep doing. Let's see. What do? You can control. Oh, right. I don't usually use Studio, but okay. So here's a histogram of our variable. Again, you can see that I always believe in starting with very simple descriptive statistics. First thing I always do is I just look at the variables in the most simple, naive kind of way. If somebody can someday answer for me why histogram always has trouble with the y-axis, I've never been quite sure why that is. So let's look at this histogram, but not only as a histogram, but let's remove this comment and look at a frequency-based histogram, or a density-based histogram. Again, I did it. Control Enter. So there is the same histogram, but shown where the bars sum to 1, and let's put a density line across that. Use the kernel density line to represent frequency. So the interesting thing about this variable, and again, you should do this for all the variables, but for this particular one, the interesting thing about this variable is that it's bimodal. There's a mode around 0.1 and another mode around 0.7, which is highlighted by that density. So let's just look at a plot of that variable itself. Most of you have seen, I'm sure all of you have seen this plot in one form or another. We can see that the temperature anomaly is around 0 in the 60s, and then it begins to increase in around 1975 or 80, up to about 1 in the year 2020. One of the things I like to do in displays is to use a nice heavy line and to use heavy fonts for any of the annotations. But let's look, instead of looking at this variable as a line in which each of the points is interpolated, let's just look at it as a series of points. And I'm going to roll this code up again. So I'm going to plot it instead as instead of the default, I'm going to plot it just as a series of points. The reason I like to do this is that it shows the data in their true raw character. We can see an observation for each point. We don't need circles, which is the default symbol for a scatter diagram, because these points are never going to overlay on one another, because time series are stretched out 1 per year. So we're looking, and then we're essentially, in a naive kind of way, trying to describe what this phenomenon does over time from 1950 to about 1920. And for the next few minutes, what we're going to do is explore various ways of not only visualizing the data, but estimating what's going on with it. First thing I'm going to use is the filter function, which is part of base R, an extremely useful tool for taking what are sometimes called moving averages, and I'm going to create a moving average based on a width of 11 years. So essentially it just is a moving window across the data, and it creates a line. I think it's about 100 observations. We can actually look at what those are. Let's do head on moving average. I guess no, this just gives us an observation for each year. I was thinking again about the density function. So this gives us a time series for each observation. And if we place that line on top of the data, we get a smoothed value. This is not a low S smooth, but it's simply a moving average. And the advantage of moving average is that many people are used to seeing that kind of a data visualization tool, so they can kind of get a sense out of what's going on. Now the other thing I like to do with almost any data where there's any kind of a trend is fit it with a linear model. So let's just run fit, and I'll put it in parentheses so we get the results of fit. And we can see, if we move the window a little, we can see that the coefficient of that fit variable is 0.01, which means that every year temperature increases by 1/100 of a degree centigrade. So over the course of 100 years, it would increase by 1 degree. That's over the entire period. And if we want to know what the R squared of that variable is, we can do a summary on the fit object, and the second to the last line shows that an R squared fits those points by about 0.87. So let's add that line. It's very simple to do that. We just take the fit object and feed it to AB line, and we get a line in a bright orange line. I don't know whether that's visible. Maybe try blue. Okay, there's a nice bright blue line that fits the data with an R squared of about 0.9. And let's add a legend to that graphic. Again, I'll roll this up. So the legend is just put in the top left corner of the plot area, and I've formulated the legend to show the points and the 2 lines. It's a little big for our purposes, but you can see the data point, the moving average with an identification as being based on 11 years of data, and then a linear model fit with an R-squared of about 0.87. If we can, fit actually creates 12, it creates a list of 12 objects, and among which is the residuals from that data. And so the first thing we've done, first thing I've done otherwise, I don't know why I'm giving you credit, the first thing I've done is I've extracted from the data the linear trend. So let's just look at the residuals from that trend. Again, it's not a time series in this case. It's simply a linear model residuals. It's a set of observations for each year, but it's not a time series. And I'm getting a 4-minute warning. Okay, so let's just print look at the residuals and plot those residuals. And you can see that there's a considerable amount of positive variation or positive residual at the beginning and the end of the series, because the series is not linear, but is curvilinear. Let's just look at the differences in those residuals and plot those. Looks kind of random, but there are many more positive residuals than there are, or there's significantly more positive residuals. Differences, I'm sorry, there are more positive differences than there are are there any questions, by the way? As you can see, we're about halfway through this script, so I'm certainly not going to finish it. I'd rather entertain a question or two.
I have one question.
Okay.
And it is, can you explain more what this 11-year moving average means? So for example, in 1980, the point there is the previous 11 years or the previous 5 and the next 6 ones. Thank you.
Yeah, the moving average is, it's plotted. You can select where it gets plotted, but as you can see, because it's a moving average that ends, it ends 4 years before the end of the data set, and it begins, or 5 years after the beginning of the data set. So it's centered on the middle of the 11 years. Is that a sufficient explanation?
Yes, thank you.
Okay. Other questions? So this demo goes on and on. I look at some correlations among the data sets and so forth, but I strongly urge you to go to the website, download the data, download the script, and tear the script apart, run the data on another series. For example, you could run it on the solar constant and look at what's happening to the watts per meter that is generated by the sun. You could look at the precipitation data, any of the other 7 or 5 variables that you want to look at, and get back to me with ideas. I think it's a unique data set because it's in one place are assembled 6 of the important World Series that I all think we should be conversant with. Everybody should know what's happening with those 6 variables.
Thank you so much. Also, if the audience wants to connect with you, is your contact information on your website?
Yes, it's right at the top of the website.
Fantastic. Thank you so much.
Okay.